Hello everyone, welcome to Gate Pass. In this video, I am going to take the remaining two problems that appeared in Gate 2015 and which were related to thermodynamics. So let's directly dive into the problem. So I will go through the problem statement. It talks about a binary mixture of component 1 and 2 that form an azeotrope at 130 degrees centigrade. And they give you the information that the mole fraction of component 1 in the liquid phase, that is equal to 0.3. Okay, further they give that the non-ideality in the liquid phase is described by these two equations, that is ln of gamma 1 is equal to a x2 square, ln gamma 2 is equal to a x1 square. Further they give that the fugacity coefficients of component 1 and 2 in the vapor phase. So now they are talking about the non-ideality of the vapor phase. So that is for both the components, that is equal to 0.9. Further they give the information that the saturation pressure at 130 degrees centigrade, that is at the temperature at which azeotrope is formed, the saturation pressures of component 1 and 2 are 70 bar and 30 bar respectively. And they have asked you to calculate what is the total pressure in bars when these azeotropic conditions exist. Okay. So, it's a very simple problem, even though it brings in lots of things in it, like it talks about activity coefficient, fugacity coefficient, azeotrope and everything. But believe me, this is a very simple problem, and let's directly start solving it. So, the first information which was given is that x1 is equal to 0.3. So, I can directly write x2, that should be equal to 0.7. Since it is forming an azeotrope, then so this is a constant boiling mixture. What do you mean by that? It means that when you heat the liquid which has this composition, then it will form a vapor phase which will have the same composition. So then what it means is that it will have y1 equal to 0.3 and y2 will be equal to 0.7. Okay, so liquid phase and vapor phase, they will have same compositions. Okay, now you have solved such problems when you have vapor liquid in equilibrium. What you do? You use either Henry's law or Raoult's law. Okay. So now I am going to write my modified Raoult's law. It will be equal to, let's say for component, I will draw a line. Okay. So for component 1 it will be y1, phi1 cap, P, that is the total pressure, that is equal to x1, gamma 1, P1 sat. Okay. So, I can use this equation to find my total pressure if I know my gamma 1, which I don't know right now. Okay. I will also write down my Raoult's law or modified Raoult's law for second component. And it will take a similar form, except that the subscripts are now 2. Okay. So, this is the only thing which we are going to use from thermodynamics. Now, see over here. Okay, y1 is equal to x1, so this I can cancel from both the sides. Similarly over here, y2 is equal to x2, so I can cancel it from both the sides. Okay, so I am just simplifying my Raoult's law right now. So what I can write now is phi1 cap p, that is equal to gamma 1 p1 sat. Similarly, phi2 p, that is equal to gamma 2 p2 sat. Okay, so I have these two equations now. Let's look at these two equations carefully and let's see the left hand side of this equation. Phi1 cap is equal to phi2 cap and the total pressure will also be the same. Okay, that means the left hand sides are equal. Phi1 cap times P, that is equal to phi2 cap times P. That means I can equate the RHS. Okay. So I can equate it and write gamma 1 P1 sat, that is equal to gamma 2 P2 sat, the saturation pressure. Okay. Then what I can do is, since I know P1 sat and P2 sat, let's take the known terms on one side and the unknown terms on another side. Okay. So I'm going to write gamma 1 by gamma 2, that is equal to P2 saturation upon the saturation pressure of component 1. Okay, so this is one of the equation which I am going to use. Now I have a relation of gamma 1 and gamma 2 in the form of gamma 1 by gamma 2. Let's bring another equation which has a similar form. Okay, how can I bring it? I have these two equations now. So let's come back to this. ln gamma 1 minus ln gamma 2. ln gamma 1 minus ln gamma 2, that is equal to a times x2 square minus a times x1 square. Or this is ln, so I can write equally well as gamma 1 by gamma 2, that is equal to a times, a is common, x2 square minus x1 square, which I can write as a square minus b square. So that is x2 minus x1 into x2 plus x1. These are mole fractions in the liquid phase. Their summation should be 1. So this is 1. x2 minus x1, 0.7 minus 0.3, that is 0.4. So what I get is ln of gamma 1 by gamma 2, that is equal to 0.4 times a. Okay, so where is this leading us to? Let's see. Now I don't know a, but from this equation I can do one thing. I know gamma 1 by gamma 2 from this equation. Okay, so I can put it over here. So instead of gamma 1 by gamma 2, what I can write is, I can write this equation as ln of P2 sat upon P1 sat. Right? Now what is P2 sat? That is 30. P1 sat is 70. So 30 by 70 or 3 by 7. So what I have is ln of 3 by 7. Okay? Now a can be calculated then as a, that is equal to ln of 3 by 7 divided by 0.4, which gives you minus 2.118. So I have calculated my a. Now the problem is solved because you know a. So I can put it in this equation and find gamma 1. Once I know gamma 1, I can put it in this equation and find p. So let's do that. Okay, and then the problem is solved. So I will just retain the value of a and erase everything. Okay, so see, let's find out. So ln of gamma 1, that is equal to a, that is minus 2.118 multiplied by what is x2, that is 0.7 whole square. So that means my gamma 1, that is equal to 0.354. If I put this value of gamma 1 in this equation, what I get is that 0.9 times p, that is equal to 0.354 times what is P1 saturation? 70 bar. So from this I get my value of pressure as 27.53 bars, which is the answer. Okay, so let's move on to the second problem. In this you have your molar residual Gibbs free energy GR, that is related to molar residual volume by this equation. Okay, further they tell you that this gas, it also follows your Virial equation of state, which is given by Z is equal to 1 plus Bp by RT. B is your second virial coefficient. It gives you two body interaction. Its numerical value is given. So B is equal to minus 10 raised to minus 4 meter cube per mole. They have asked you to evaluate what will be GR at 27 degree centigrade and 0.2 megapascal. So the only concept which you require in this case is how do you define your residual properties. Okay, so you define your residual properties in general. If M denotes any extensive property, then I can write the residual property as M minus Mig, where M is the property of the real gas minus the property of the ideal gas. Okay, so if I am writing my molar residual volume, then it will be equal to molar volume of the real gas minus molar volume of the ideal gas. Now how do I write this these two quantities? Let's make use of this equation. PV is equal to Z RT. Okay, so for real gas, my molar volume will be equal to ZRT by P. Okay, and for ideal gas, since Z will be equal to 1, so I can write my molar volume as RT by P. Okay, so now I plug these values in this equation. Okay, so I write my molar volume, molar residual volume as Z RT by P minus RT by P. RT by P is common, I can take it out and I can write Z minus 1 is in bracket. Okay, so my molar residual volume is this quantity. That is the only thing which you require from thermodynamics to solve this problem. Remaining else is mathematical manipulation. Okay, now I don't know Z, but I know this equation of state. So what I will do is, if I take 1 over here, so it will be Z minus 1, that will be equal to BP by RT. So I am going to replace Z minus 1 using my Virial equation of state. So now this equation becomes RT by P multiplied with BP by RT, because this is equal to your Z minus 1 from Virial equation of state. RT gets cancelled, P gets cancelled, what you are left with is only B. So your molar volume is only equal to B. Now I am going to take this value and plug it over here. Okay, so I have GR by RT, that is equal to integral 0 to P, VR is nothing but B by RT dP. What you will observe is that B is a function only of temperature, so you can take it out from the integral. RT is also independent of pressure, you will take it out. Okay, in fact RT on both sides will cancel. Okay, so what you are left with is only this equation. B take out, so 0 to P dP integrated, what you get is BP. Put the values. What is B? Minus 10 raised to minus 4. What is P? 0.2 megapascal, so 0.2 into 10 raised to 6. And what you get is 0.2 into 10 raised to 2. Of course there is a minus sign, so you get minus 20, and this is joules per mole. Okay, so this was asked, you had to calculate GR, and that's what we have calculated. I hope you learned something from this video, and if you liked this video, please don't forget to like this and subscribe to my channel. Thanks for watching.